Do you like have your ass down? Some people like very well thought out. So personally, I think the first one is a little harder. That's the for the two gun is not too bad. The second easiest is the square. Good. For the square, you can just solve it face down, but then all the other ones are so bad. The first one is Sergio? Proceed over there. Good afternoon, everybody. So I think this slide already shows what Boris is all about. He has been both the, shall I say, brains and muscle behind this experiment, meaning that he has not only contributed intellectually to this effort to build an optical transition clock for the very first time ever that will work beyond the standard quantum limit. But not only has he contributed many ideas, he has also built and engineered very well many of the various devices, lasers, locks, etc. that we need for the system to work at a level where now I'm very, very confident that we will have some very beautiful results in the future. So Boris is as much as an engineer as he is a creative scientist, and I'm sure you'll see a lot of that in this presentation.
Thank you very much, Levin. So let's get started. And the first thing we do is we clean up the slide a little. So I want to tell you about the work I've done the last 6 years here at MIT on cavity quantum electrodynamics with ensembles of Ytterbium 171. And if any of those words don't make sense, hopefully by the end of the talk, you'll understand them a little bit better. So here's a brief outline. I'll start by telling you about what clocks are and how they work and how quantum mechanics comes in. Then I will tell you about optical cavities and how you can use the phenomena of quantum electrodynamics to create entanglement among these atoms and thereby improve clocks. Then I will tell you about our apparatus, which I think is pretty cool. And then I will highlight 3 really neat experiments that we've done to show the kinds of control that we exert over our system. And I will then wrap up by telling you about some of these really exciting future directions that we're thinking about. All right, so what is a clock? If you pick out any clock you have, there's only 2 parts in it. The first one is something that happens regularly or repetitively. And the second thing is you just need a mechanism that counts these oscillations. So if you have a nice mechanical wristwatch, which I don't have, the components in there, there's some kind of pendulum, which oscillates back and forth, and there's a bunch of gears, which allow you to convert this periodic oscillation into a usable readout. So how do clocks look like historically? If you go to the very beginning, people had a very deep interest in measuring time because it's allowed them to predict things like when the rain will come, how to get around, things like that. And the first kind of clock people had were just observations of the sun and the stars. And even with this, people managed to do pretty well for themselves. They built sundials. But it turns out that a sundial, even though it seems so perfectly regular, the sun's motion across the sky, it turns out that depending on the season, this will be off by a few tenths of a minute. And in addition, it doesn't help you measure very short periods. So the next thing people came up with is things like hourglasses. And if you were teleported to sometime before the middle of the 17th century, the best clock money could buy was going to be a water clock. It's just one of these jugs that has water coming out of it, and you just track the level of water. And the thing that limits the accuracy of these devices is actually the fact that the viscosity of water changes with temperatures. So 1 degree Celsius is about a 3% change, so your clock will run fast or slow. And interestingly, you associate hands and a dial with a mechanical clock, but it turns out those were actually invented several centuries before mechanical clocks and pendulators. So as I alluded to it already a couple of times, something very exciting happened in 1650, which is that the pendulum clock was invented. And you probably know the story of how Galileo was observing the chandelier swinging back and forth in the cathedral and comparing to his pulse. And he was right that pendulum oscillations are very regular. And the first prototype was built by Huygens in 1656, and already it was accurate to 1 part per thousand, which was better than any previous clock that anyone had ever built. And over the next 3 centuries, people invested a lot of time and money into making pendulum clocks better and better. And this photograph here is the best clock, the best mechanical clock ever built. There's a pendulum oscillating freely inside a vacuum chamber, and then there's a normal grandfather clock that's synchronized to it. And so with these kind of devices, people realized an accuracy of several parts per billion. And this, these have already become astronomical timescales, and in fact, they are astronomical. You could, with a clock of this accuracy, you can detect fluctuations in the Earth's orbit because of gravity from other planets in the solar system. But the quest continued, and so people started developing other kinds of clocks, and these are the things you will find in your pocket or in your wrist. And any kind of quartz watch has a tiny little quartz tuning fork, and you simply use the fact that it's a crystal, and so its size doesn't change over time, and has some resonant frequency, and you can measure it with electronics very precisely. So they're cheap, they're abundant, they're great, and if you look at your wristwatch, it will probably be accurate to about 30 seconds every year. There's 1 part per million. And if you spend a few $1,000s and buy a synthesizer from a reputable company, it's going to be a few orders of magnitude better, and then people have developed even more fancy versions, which are good to about 1 part in 10 to the 14th. So the thing that plagues all of these tuning fork-based clocks, or oscillating crystal-based clocks, is that they're fundamentally based on a physical art method, which means that their accuracy is limited. You have no guarantee that the crystal didn't shrink a little bit, or a few atoms didn't fall off of it, and now it's different than it was yesterday. And so the next step in the evolution of clocks, which brings us to the present day, was the idea of atomic clocks. And so why are atomic clocks great? There's 2 things. The first one is that the effective pendulum is the oscillation of internal states of atoms, and those happen much faster than any physical device you can build. And the second thing is atoms are the same from day to day. An ytterbium atom yesterday, and the ytterbium atom tomorrow, and the ytterbium atom in a galaxy far, far away should presumably all be the same. And so that is the motivation for these clocks. Unfortunately, the technology for actually building them was not developed until World War II. But after that, people quickly caught up, and the first fully functioning atomic clock was built in the mid-1950s. And already you see that this first prototype, so to say, was better than any previous clock, which shows kind of how these ideas and new physical systems really drive progress in this field. And only 12 years later, people realized this was a much better way to define the second. And so the second was redefined by saying that a certain transition frequency in cesium was going to be this number. And that's the definition of the second to this day. So here is a log linear plot of the uncertainty of these clocks. This is nanoseconds per day. So this is 1 nanosecond per day. And this photograph, I actually took it in Washington, D.C. You can go to the Smithsonian Museum, and you can find the world's best clock 20 years ago collecting dust in a museum. I think they keep it pretty clean, so it's actually in good shape. So this shows, again, how fast this technology evolves. So the next generation of clocks, which really bring us to the present day, are these optical clocks. And basically they're the same as a microwave atomic clock, but instead of interrogating a microwave transition, you actually use an optical level. And what this gains you is that you have a much faster oscillation in your clock, and that helps you divide time ever more finely, and that gives you an improvement in precision. So it's about a factor of 10 to the 5. The main technical and engineering challenge is building very stable lasers, which I think has been a very active field in the last 20 years, in large part motivated by these clocks. And the first realization of these clocks was with trapped ions. So you simply have a single trapped ion, and you can interrogate its internal structure. Why is this good? Because people are good at trapping ions. But why is it bad? Is that there's only one ion that you're probing, so you don't have that much signal. So to improve the signal, the next and most modern generation of clocks are so-called optical lattice clocks. So essentially you have an ensemble of atoms, and you have a standing wave of a laser beam, which traps these atoms in its attractive potential. And so you gain in precision because you're now measuring many atoms. So there are two physical principles that allow these optical lattice clocks to work. The first one is by putting the atoms in an optical lattice, you can suppress Doppler shifts. So just to give you a few numbers. Typically, the transition frequency, so the rate, the energy of this splitting, is on the order of 10 to the 15 hertz. And the Doppler shift corresponding to an ultra-cold atom at 1 microkelvin is about 10 kilohertz, which means that if you want to do spectroscopy better than 10 to the 4 divided by 10 to the 15, you need to somehow prevent this Doppler shift from happening. And so what you do is you trap the atoms using an optical lattice, which confines them so tightly that the Doppler shift is removed. Okay, so then the second thing that you need to deal with is now you've trapped your atoms in a lattice, you have confined them, you're mechanically exerting force on them, and it's possible that the energy shift of this ground state and energy shift of the excited state are going to be different. So now, depending on how you're trapping or how strong your trapping is, the energy will be different. So you have gained nothing. And that's where the idea of a magic wavelength optical lattice comes in. So these magic wavelengths are particular wavelengths of trapping light for which the energy of the ground state and the excited state are shifted by precisely the same amount, regardless of the intensity of the trapping. And so with these two physical insights, optical lattice clocks can be realized. So what are these things good for? I think all of you have benefited from atomic clocks, because anytime you drive anywhere with GPS, that's how it works. And of course, there's other, perhaps less day-to-day applications in very precisely sensing the shape of the Earth. For example, you can measure the melting of Greenland's ice sheets to how much the gravity exerted by those ice sheets changes over time. But we're a crowd of physicists, and physicists love fundamental questions. So anytime you build an atomic clock and you send it into space and it flies around, that's a free test of general relativity. And GPS satellites have actually served as one of the most stringent confirmations of general relativity. Another thing you can do is you can take these clocks that are very precise, and you can look for violations to the standard model of particle physics, which would cause different clocks to tick at different rates, depending on their structure. And in addition, you can even look for variations of fundamental constants. So in physics, there are constants you might know of, like the speed of light, which are not really constant because they just relate units that people have defined, like the meter and the second. They're completely arbitrary. But there are also dimensionless constants, which are really given to us by nature. And if those change, that tells us something very interesting about the structure of the universe. All right. So now we have to do some quantum mechanics. Prepare yourself. All right. So atomic clocks, in their most current generation, operate using what's called Ramsey spectroscopy, after a fellow named Norman Ramsey. And all the quantum mechanics you need to know is that there are two levels, a ground state and an excited state. And in physics, we like to call this a spin one-half system, because a real spin one-half system also just has two energy levels. So there's a ground state and an excited state. And we like to represent these states using the so-called block sphere. So the ground state is on the ground, and the excited state is on the top. And in quantum mechanics, you can have superpositions of states. So for example, if they have a plus sign between them, we say it points in the plus x direction. And if there's an I, it points in the y direction. There's any possible state that's a superposition of these two can be expressed on this. And the Ramsey sequence basically allows you to compare the rate at which your atom is oscillating and the rate at which your laser or microwave source is gaining phase. So what you do is you initialize your atom in the ground state, you excite it with you rotate the state to create a superposition, then you wait for some time. This is time tau, it's called the Ramsey time. And there's two things that are happening in this time. The first thing is that your laser phase is evolving, and the second thing that happens is that your atomic phase is evolving. And the phase that you accumulate here is just the difference. And then you do another rotation, which allows you to convert this rotation in the phase direction to a rotation in the population direction. And lo and behold, now you have a usable signal. The phase is just the Ramsey time times the frequency difference. And that's how you use a Ramsey sequence to stabilize the frequency of a laser to your atomic transition. Okay, so then the next slide should be really easy. All we're doing now, instead of having one atom, we have n atoms, where n is some number like 1,000 or a million. And all this does is now instead of having, now you basically have some kind of statistical distribution in which direction the spin points. Everything else is exactly the same. You start in the ground state, you do this rotation, then you wait some time, you do another rotation. And if you're taking notes and you only want to write down one thing from the talk, here we go. This is the thing I should have put in the box. So this tells you everything anybody knows about clocks. The stability of a clock at this so-called standard quantum limit is given by some prefactor A, which is more than 1. And it can be equal to 1 if your experiment is really good. It's just a technical parameter. Then the next thing is the transition frequency. So the faster you're ticking, the more stable the clock. And then the next three terms are big T is the total amount of time you've been doing the clock experiment. So it's basically how many hours I've been in the lab. Capital N is the number of atoms you're measuring. So more atoms is better. And little tau is, as I said, the Ramsey test. So this might seem opaque, but you can rewrite this. And trust me, I did my algebra right. There's three terms in this expression. There's the signal, so number of atoms times the ticking frequency times how long you were waiting for the comparison. There is the noise, which is how good your technical skills are, and some irreducible factor of root n we'll come back to. And then this is the number of experiments, because there's t total time and tau per experiment. So what you see is the precision of the overall clock scaled as 1 over the square root of the number of atoms that you have. And this is called the projection noise, or the standard quantum limit in atomic clocks or any kind of clock. So the interesting thing is atomic clocks, because they operate with such a simple underlying clock mechanism, you can fully understand the limits of the precision. Unlike normal pendulum clocks, if you imagine measuring the position of the pendulum ever more precisely and doing tricks, the atomic clocks is very straightforward, which is nice. So here's one of my favorite diagrams. This shows the state of the art in atomic clocks. This axis, the stability at 1 second, is if you have two of these clocks and someone only gives you access to them for 1 second, how sure are you that they're ticking at the same rate? And this y-axis is the same thing, except you have all the time in the world. And so this is basically the precision, and this is the accuracy of your clocks. And there's three kinds of points on here. The first one and this rubidium-87 and cesium-133 are microwave transition clocks. And so what you see is that their short-term stability is bad because they operate with a low frequency under transition. But their overall accuracy is actually pretty good. And the reason is that this technology has been around for 50 years, and people have really perfected how to make their clock work for years at a time without breaking. The next group of clocks are these single ion clocks. And so here you see the precision is improved already by a factor of 100. Even though you have much fewer atoms, your frequency is much higher, so you gain. And there's a whole range of how stably people have operated with them. And then finally, in this bottom left corner, which has high precision, and high accuracy, are these optical lattice clocks. So here you can kind of see how this formula lets you understand the state of the art in one simple diagram. So now you're going to be like, well, Boris, who cares? You know, quantum noise, classical noise, doesn't really matter. But actually, it turns out that the state-of-the-art optical lattice clocks are actually quite close to this quantum. So here's a paper from Gilla in Boulder, and here this dashed line actually corresponds to this quantum projection noise, which is the same as the quantum noise we're measuring. And it turns out that there's a lot of other quantum sensors that are also operating with a precision that's limited by the quantum noise. Okay, well, I've clearly set up the field for an easy putt. How are we going to fix this? Well, the idea here is the thing called spin squeezing. And so the idea is you start with this initially round distribution of quantum noise. So there is noise this way and noise that way. And in quantum mechanics, you probably know there is the uncertainty principle, which means that there's some basic amount of noise you can't get rid of. But what you can do, you can redistribute the noise. And when you're operating a clock, the only thing you care about is this phase direction. And this other axis doesn't matter. It doesn't contribute to your signal or to your noise. And so that means that if you just build a clock that operates like this, with the squeeze state, what you get at the end has a smaller noise when you read it out. So basically you're measuring this projection of the state, and you will get less noise. All right. So now we get a little more technical. How can you make this spin squeezing? And one approach is to use this so-called one-axis twisting Hamiltonian. But basically, it's a nonlinear Hamiltonian that corresponds to atom-atom interactions. So the energy of the system is nonlinear in the total state. And in this blocks sphere picture, you can understand it the following way. If you didn't have the square, if you just had h bar sv, that corresponds to the state rotating around. But with sz squared, what you get is that the top rotates a little faster, the bottom rotates a little slower. You can see that this round state eventually becomes elliptical. And if you like quantum optics, this is the same as optical squeezing, disregarded if you don't care. All right, so people have actually done this using microwave clocks, both in our group a few years ago and also out in California. And so it works. So you can see that this dashed line is the standard quantum limit, and then this dashed line is also the standard quantum limit. And people have managed to improve their microwave clock by about a factor of 10. So we want to do the same thing, but using an optical lattice clock, because that will really push the frontiers of precision approach. All right, so the next thing I have to tell you is how we can use cavities in order to create these entangled states. So an optical cavity is just two mirrors, and all this does is it confines light and forces it to bounce back and forth many times. The number of times it bounces is called the finesse. And in quantum mechanical language, this is a very simple system. There's only a few parameters that describe it. There's the rate, kappa, at which photons can escape from the cavity, or get absorbed, or anything bad. Gamma is the rate at which an excited atom will spontaneously emit light into free space, and then you no longer have it. And finally, G is the interaction rate between the cavity light and the atomic state. So basically, G is good, gamma and kappa are bad. So there's a dimensionless number, which physicists love, which is the ratio of good to bad, and that tells you how strong the interactions are between the light and the atoms. It turns out you can express this geometrically, and the only thing that matter are the finesse, so how many times you can reuse the same photon, and how narrow the beam inside the cavity is. So one thing that I think is often overlooked in these experiments is that actually almost everything we do is positive. And here's what this means. that the result of your experiment will only depend on the product of this single atom cooperativity and the number of atoms in it. Which basically means that it doesn't matter if you have 100 atoms with a coupling strength of 1 or a million atoms with a coupling strength of 10 to the minus 4. All your experiments will look the same, except, oh yes, this is my coupled pendula thing. That's exactly what happens. You basically have the atoms, which are like a pendulum, and you have the cavity, which is like another pendulum. And this coupling strength, G total, which is G times the root of the atom number, is just how strongly they're coupled. And if you remember Mechanics 101, if you have two pendula that are coupled, they will have two eigenmodes that will be like this and like that, and their frequencies will be split. And this thing that people often describe with quantum mechanics and call it the vacuum-Rabi splitting is nothing but coupled pendulum. So the thing that does depend on the quantum nature of your atoms is the fact that you will have noise, this projection noise. If you have 100 atoms, there will be an error of plus minus 10 atoms that you cannot get rid of, no matter how well you build your experiment. That's the thing where quantum mechanics comes in. All right, so there are three known ways of producing spin squeezing. The first one is actually to use a quantum non-demolition measurement, which is a fancy word to say that you prepare initially classical state, and then you measure the SZ value, which is basically the number of atoms in a certain state. And if you do it without measuring which specific atom is in this state, that actually will project through the bizarre ways of quantum mechanics the state into a state of reduced width, which is a squeeze state. This is very useful because the good measurements are always good. The second method is this feedback-based squeezing I mentioned earlier. And it has a similar scaling with experimental parameters as the measurement scheme, but fortunately, even if your detectors are not perfect, you can still do a good job of squeezing. And finally, you can use dissipative methods, which I'm just putting here because they're really cool. All right, so how are we going to make this nonlinear Hamiltonian? Basically, what you need to do is you have to make each atom influence all the other atoms somehow. And so the way we can do this, there are many ways, but here's one. Here's the level diagram that we have. So this is the atomic resonance, just the pendulum. Here's the cavity resonance, also just the pendulum. And what we do is, before we even send in the laser light, it turns out that because of the interaction of these two pendula, the resonance frequency of the cavity will shift slightly. One way to understand this is the cavity is a couple of mirrors, and the atoms are basically a piece of glass, and that will introduce a phase shift for the light as it bounces back and forth, which means the frequency will change. And so then what we do is we send in a laser beam on the slope of this cavity, and that means that now, depending on the atomic state, there will be a shift in the cavity frequency, and that means that there will be a shift in the amount of light that manages to get into the cavity. So that's what I just said. Of course, just like the atoms are influencing the response of the cavity light affects the energy of the atom. So basically, when you get more photons, the atomic energy also gets shifted. And so now what we see is that the energy per atom is proportional to the intensity of light, as you expect naively, and that's proportional to the atom number through this collective cavity shift mechanism, and that gives us the desired quadratic Hamiltonian. Magic. All right, so if you want to do a good job of spin squeezing, it turns out you only need this dimensionless coupling strength of 1. But if you want to make a more interesting quantum state, you need a larger value of this cooperativity. I will get to this at the end of my talk. So what does the field look like? As you can see, it's a really popular activity, doing squeezing and entanglement these days. So I just want to point out that, so these stars here are with trapped ions, but these are basically guys that are doing quantum computing with ions. These red dots are using Bose-Einstein condensates, and these blue ones are most similar to what we're trying to do, and they use very cold but not quantum mechanically condensed atoms. So all of these experiments, except for the trapped atoms, are done with rubidium, because rubidium is a really fun atom to work with. It's really easy to work with. The one exception is not shown on this diagram, so I have to add it, and it was in this paper. So what we want to do is do this with ytterbium. So why ytterbium? What is ytterbium? It's a good question. It's element number 70, and it's really cool as an atomic physicist because it has 7 stable isotopes, about a number of bosons, and 2 are fermions, and it's useful for a clock because it has 2 valence electrons. And these 2 valence electrons can be paired, And that produces optical transitions that have very narrow lines. And that's good for building a clock. Maybe it will be easier if I show you a periodic table. Here's ytterbium hiding in the corner. And the things circled in blue are its buddies that also have 2 valence electrons. Oh yes, you saw what it looked like. It's kind of nondescript silvery metal. So if you're an atomic physicist, this is what ytterbium looks like. It's just a bunch of energy states and some wavelengths of lasers that you need to buy or build to make your experiment work. And the reason why ytterbium is so great for our experiment is this transition, which for very good reasons has a very narrow line width. This is 7 millihertz. And the absolute frequency of this transition is one of the most precisely measured values that people have ever measured. It's given by this 518 terahertz. I'm not going to read the rest of it. So as you can see, this is 16 digits of precision. And these optical, this is not why this is a good clock, but because this transition is good for building a clock, are we able to do so? And we, I mean the collective we, not we personally. All right, so now I will tell you about our apparatus. We use what we call an asymmetric micromirror cavity. Okay, so what's the deal with this? We started building the apparatus 6 years ago, and we're thinking to ourselves, we want to do spin squeezing, but we also want to do the interactions that are strong. And these are kind of competing demands, because if you want strong interactions, you need to confine the light really tightly. But if you want to do spin squeezing for a clock, you need to have a lot of atoms. And if your light is tightly confined, you have a lot of atoms that doesn't really jive together. But then we pulled out our textbook on optics, and we did some calculations, and we found that if you have, so these cavities are literally just 2 mirrors placed in front of each other. If you have one mirror that has a very small radius, and the other has a large radius, you can actually find a parameter regime where the cavity has a large length, but it also has a strong interaction because the light is still tightly. So this is kind of a schematic diagram of what it looks like. And this is why we chose this design. So let me tell you about these optical micromirrors because they're pretty cool. You just take a pulse of CO2 laser light and you shoot a flat piece of glass, and it produces a really smooth dip. This is what it looks like with a microscope, and this is what it looks like if you scan a very sharp point to get across it. And the good thing is that because it's made in such a thermal and violent process, the surface actually melts or evaporates or some kind of black magic. It's very smooth, so it's good for making a high-quality optical cavity. Okay, now it's time for show and tell. So this is not the actual cavity we're using in the experiment, obviously. I know, right? But we did not know anyone who had built this kind of design, so we decided we would try to build the prototype before we built the real thing. Here's the prototype. I will pass it around. So you will see, oriented like this, that's the correct orientation. On the bottom, there is a 2.5 centimeter radius of curvature mirror, and on top, there is a flat glass rectangle. And if you look at it just right, you will see 6 tiny little dots going down in a line, and these are the micromirrors. Please pass it around, don't drop it, be nice to it. All right, so this was the kind of the real thing. And so then for the real cavity, we could calculate the expected coupling strength, and in these dimensionless units of the cooperativity, if we put the atoms really close to the small mirror, we could expect a dimensionless coupling strength that was on the order of 30 or 40, which is really high by the standard of these experiments. But on the other hand, we could also tune the coupling strength to the factor of 1,000 just by moving the atoms a few millimeters. So this was a really unique and very useful feature for our apparatus. So this is the slide that's like a training montage in an action movie where they show you the guy like running up some steps, but that's not really how much work it takes, you know, to train to box with someone. So I'll just show you 3 pictures. This is what the lab looked like 6 years ago, almost exactly. So we had a nice empty floor and some garbage in the corners. And then 3 years later, this is what the experiment looked like. So this was the day when we finally put in the actual experimental cavity into the vacuum chamber after some hurdles. And then this is a couple days ago, so you can see that there is a monotonic increase in the amount of hardware and equipment, which means the experiment is doing well. More gizmos is always good. Yeah, I will not dwell on this, but many fond memories. All right. So now I will tell you about three, I think, really cool things we've done with the experiment so far. So the first one is very precise measurement of the number of atoms that we have interacting with our pen. So the question that we really want to answer is how well can we measure the atoms? Quantum mechanics is a very intimate relationship with measurement, and there are certain limits on measurement quality that you can calculate just based on how strongly you interacted with your system. And another reason why we really care about this is that normally measurement will destroy your system. And if you can make your measurement better with the same amount of destructiveness, that will make your experiment work in a better way. And so it turns out our system is very simple, and you can actually model it very accurately. And we've made a lot of theoretical progress on making these kinds of calculations. And so we can calculate the quantity called the quantum Fisher information, which is also essentially the entanglement strength. And basically in all the calculations we've done, we have found kind of a one-to-one relationship between how strongly your atoms are entangled with some kind of probing light and the amount of probing photons that can scatter into free space, which makes sense. There's some relationship between the measurement, which is an informational quantity, and the scattering into free space, which represents some kind of entropy gain. So there's some really interesting relationships. We have some hand-waving ideas about why this should always be true, but in practice, we can calculate them for any specific experiment we can think of. And so this directly is useful in order to do these kind of measurement-based leading experiments. But before we get to that, I just want to show you some cool pictures. So remember this probing scheme where we have the cavity and we have the atoms, and you put the laser on the slope. Well, what happens if you just have a bunch of atoms and they gradually fall out because they hit some other stuff, they get hot. So the cavity resonance will gradually shift toward the probing frequency. And so the number of photons you detect as a function of time should go up. That's exactly what we see. And if you convert this photon number into an atomic population, just using this simple formula, no extra parameters, you get a beautiful exponential decay. So it shows that this measurement is working in that expected way. The next thing to consider is doing the same kind of probing, but near atomic resonance. So here we have the atomic state, which is the nuclear spin. And we have the excited states. We apply some magnetic field, so now we're only tracking with this level. And so here what you expect to see are this vacuum-Rabi splitting I showed earlier. And what we want to do is we want to measure how many atoms are in this state. And the way to do that is by measuring how big the splitting is. And it turns out that you can measure the power of light coming through your cavity, or you can also measure its fate. And both of them are very useful. I can tell you more about the relationship between them. And then what we do in the experiment is we apply this two-color probing. So we send one frequency of light and another frequency of light at the same time, so they are transmitted simultaneously through a cavity. And this scheme has a lot of advantages. It's very resistant to technical noise, and we can extract phase information. So Vladan likes to tell me that when I started working on this experiment, I had one request, which is that I do an experiment where I can name my photon. And this graph, I think, is a good illustration of this. Each little dot you can see here is the detection of a single photon. So, this might be Alice, and this might be Bob, and this might be Charlie. And altogether, they give you some information about the atomic state. And so this is one measurement, the blue dots, and another measurement, the red dots. You can do this many, many times. This measurement is very precise. So how precise is it, actually? How close are we to this fundamental limit of the measurement quality we can achieve? And so here's some data. The axes have really horrifying labels, so I'll just explain what they are. The y-axis is the measurement quality. Less is good. The x-axis is how close the system is to being in the most optimal situation you can achieve. And this gray line is a model which physicists really, really, really love that has no free parameters. Just pure theoretical calculation. As you can see, actually our data are slightly better, so we can fudge factor it a little, and we can agree with our results. It agrees very nicely. So that's one thing. And then, what's showing up now? Oh yes, and this dashed line here is actually the ultimate limit of measurement that we can do in our system. And so as you can see, we're only a factor of about 1.5. Okay, so the second thing, I promised you squeezing. Well, here's the squeezing. So in our system, again, we use this resonant probing scheme. And we have a bunch of very useful technical tricks to make our squeezing better. And remember, I told you we can model our system accurately. So here, for example, depending on the probing frequency that we use, we can calculate the squeezing strength, this quantum Fisher information, and the usable squeezing all in one graph. This is a very simple calculation. And this is the vacuum-Rabi splitting, except it looks different because it's on logarithmic scale. And what we do is we put the probing laser with a large detuning from these vacuum-Rabi tubes. And that turns out can generate squeezing which is more unitary, which means more reversible. And that's a really good thing, it turns out, both for quantum control and information, also for clocks. That's another really cool project we did that I will tell you about only if you ask me. So all told, just imagine that we have some way that we send a bunch of light and we implement this kind of squeezing operator. We start with a round state and we end up in this squeeze state. So how can we show that our squeezing is doing the thing where, how do I know this picture is correct and we're not just doing something crazy? So there are two experiments we can do. The first one is the so-called unsqueezing experiment. So if I'm really telling you that this is what happens and that this is a reversible operation, well, it should stand to reason that if I just flip the state a little bit by rotating it and apply the same operator again, I should be able to recover the original state. And that's exactly what we see. So this is a function of this rotation angle, theta. We see that the width of the state in this direction has a dip, and it goes down basically to 1, which is what you would expect if your squeezing operation is working well. Okay, and the second experiment you can do, well, how do I know that maybe I just didn't do anything? Or maybe I added some classical noise and then I removed the same classical noise, right? Who knows? So the way to really prove that you're doing something good is the technique so-called quantum magnification. So what you do is you start with this nice round state, you make this elliptical state, and you rotate it a little bit. And you notice that this state is narrow, which means that if you rotate it by a small angle, you can make it fully separated from the original state. And then if you apply the squeezing operator again, it turns out that the separation of these two states is going to be bigger than the separation that you applied yourself here. This is the magnification aspect of it. Lo and behold, the black line is the maximum you could possibly get without quantum effects, and the red line is what you see. So together, these give us about 7 dB of squeezing, and it's almost unitary, which is really cool. All right. So what's the next steps? Well, more squeezing, of course. So more atoms, more squeezing. We have ideas for how to improve the probing. In particular, you can reduce the detuning of your probing laser from resonance, which is more technically difficult, but should give you more squeezing. All right, and the last thing I want to tell you is how we have observed many atoms that have strong coupling. So more pictures. This is what the experimental cavity looks like inside of a vacuum chamber. And this tiny green dot, which is obscured by my laser pointer, is the mod. So now you can zoom in. So this is just taken with just a normal pocket camera. And this is maybe about 10,000 atoms. You can actually see it just with your eye. It's pretty nice. And if you use a little fancier camera, you can see a picture of the magneto optical trap. It's about 10,000 atoms at a temperature of 10 microfarad. And using magnetic fields, we can move them around as we please. In particular, we can put them really close to the mirror. So this is another picture. So this is the mod. This is the reflection of the mod. And then this tiny green dot is actually where the micromirror is. That's really where we want to put our atoms to have strong interactions between the light and the atoms. So we can take pictures of the mod, but how do we know that the atoms are actually there? So we could measure the cooperativity, this dimensionless coupling strength, by observing the phase shift. So remember, we have this spin 1/2, which points in a certain direction, and we can send in very weak probing pulses and see how much it rotates. So when we put the atoms at this smallest distance of 100 micrometers from the surface, we observe these rotations. And so just to give you an idea, here we have maybe a few hundred atoms, maybe 1,000 atoms. If you send in a single photon, then the direction in which the atom points rotates by about 10 degrees. This is a single photon influencing the behavior of many atoms, which is very characteristic of these strongly coupled systems. And then if you can do the measurement for many different distances, you see that it decays in the expected way. The black line is another thing physicists really love, a zero parameter theory curve. It's great. All right, so if we are 100 microns from the surface, and the coupling strength is about 20, can we have many atoms? The answer is yes. This is beautiful pictures of vacuum-Rabi splitting, corresponding to about 10,000 in the units of n times beta, which means that for n, we have about 500 to 1,000 atoms at this distance. So with these kind of coupling strength and atom number, we can do even more interesting quantum mechanics experiments, which I will now tell you. So what's the future? Well, the first one is to actually realize the spin-squeezed optical clock. So this is the part of ytterbium that I care about right now. This is the ground state. These are the states we've been using to do all the interactions, and this is the clock excited state. And so far, what we have managed to do is we managed to do some stuff with the nuclear spin, and then apply some light that entangles the atoms that are all sitting in the ground state. But then what you can do, it's pretty suggestive from this picture, is you can apply a pi pulse and transfer all of the atoms that used to be here into the excited state. And now the entanglement should be preserved, should be the key word. And then we can operate a clock that has spin squeeze. It's much easier to draw this on the slide than to actually do it. And then the second thing is the strong coupling regime that I talked about recently. So if you remember this dispersive situation where you have the atoms in the cavity, if the coupling is strong enough, you can be in the following situation. If you add one more atom to the system, the cavity shifts by more than one line, which means that if you have 0 atoms, the cavity spectrum looks like this. If you have 1 atom, the cavity spectrum looks like this, and so on and so forth. What you can do then is you can send just one single photon. And if you detect this photon, that guarantees that you had exactly 2 atoms in the states that you're probing. But the key thing is you don't know which atoms they were, because you sent in 1 photon, you detected 1 photon, which means that no photons were scattered or absorbed. And that means that the state still is quantum and still very pure. And so this is what's called a Dicke state, which has a certain position along this SZ axis. But it's better than that. It's very easy to generate photons that have multiple frequencies. And that means that if you send a single photon that has, say, this frequency, and then you detect it, now you've suddenly projected your state, instead of being in a single ring, you have 2 rings. And this is now a really cool complicated quantum state. And the limitation, there's nothing free, but basically, as long as the atom number is smaller than the cooperativity, you can essentially make any state you want. So we have complete control over our atoms. Okay, so now I want to kind of give you 2 paths that we could use with this apparatus to go to the Heisenberg limit, which is the true fundamental limit of measurement precision that's possible, according to quantum mechanics. So the first one is this measurement-based scheme called spin carving that I just explained to you. So what are its upsides? If it works, it works. If you detect your photon, you have the state you wanted. If the atom number is large compared to the cooperativity, you can still make really interesting quantum states. You just can't make any state. You can make a certain cool subspace of quantum states. On the other hand, we can also do this SZ squared squeezing type with the shearing as described earlier. So this is deterministic. It works. You just have to send in some light. You don't care if you detected some light or not. That's great. But because you have to send in a lot of probing light, you have to do it slowly. And that means there's more time, and environmental perturbations can ruin your quantum state. So now I want to entertain you with some animations. This is the Wigner function for 40 atoms, initially in a coherent state. And I'm going to apply the spin carving protocol with different spacings for the photon frequencies. So what you see is initially start in single state, and then you produce what's called a Schrodinger cat state. And as the amplitude of the cat increases, so this is the live and the dead part, quantum physicists are not very humorous. You see that you get all these fringes, and that the frequency of the fringes increases. So this is a maximally entangled state, and in terms of spectroscopic quality, this is as good as it gets. On the other hand, with this one-axis twisting, you can do the same thing, but it looks much wonkier. So watch. So now this is versus time, and see how magically we obtain the same final end state. So indeed, there are many ways to attain this quantum limit, and in our system, we can hope to implement many. All right, so now I want to summarize what I did. So we've built this beautiful, versatile cavity QED atomic clock apparatus. We can do these quantum measurements very close to the ultimate limit. We've demonstrated this unitary or near unitary squeezing. We can have large atom numbers with strong coupling, which pave the way to building an optical clock with squeezing and generating very interesting things. So now, something different. Since I have so many of the people that I care about so much, I want to provide you with a different kind of entertainment. So just bear with me. I've been here for almost 2,300 days. It's been a wonderful 6+ something years. I counted. This is how many emails I've received, and I delete my spam. So this is non-spam emails. And of those 105,000 emails, about 50 were bizarre physics theories, things that claim the Higgs boson is some weird atom, stuff like that. Those of you who have received those emails know what I'm talking about. I've sent 14,362 emails. This is current as of a few days ago. We have collectively in the lab built 176 of these electronics project boxes. And this is only the ones that we bothered giving a serial number to. So there's a lot of little project boxes that are not counted. And I built 47 of those. We bought 613 half-inch. And here is a graph of the number of posts bought versus the length. As you can see, the 1.5-inch post is clearly the winner, and it really drops off after 4 inches. We bought 330 mirror mounts, and those of you who have had the chance to work with me know that one Thorlabs mirror mount, which is $40, is one quantum of money. And I consider anything less than $40 to not be worth thinking about when you decide if to buy it or not. And then to build all of these 176 electronics boxes, we have purchased about 850 of these BNC connectors. All right, so here are some Borisisms to keep you entertained. Everything is linear to first order. Nothing wastes as much time as a broken cable. Experiments are never wrong. Only our interpretation of them could be. An unlabeled optic is a worthless optic. The temporary becomes permanent. Always use the right tool for the job. And finally, if it was easy, someone else would have done it for us. All right, so now this brings me to a slide where I might start crying. Many people who merited inclusion here are not on here, and that's not to say against you. It's just that there's only so much space on the slide. So first I want to thank all the people that I've had the privilege of working with in the Ytterbium Clock Lab, especially my brother in arms, Akio, who basically started the project with me 6 years ago. And, it was like going into a junkyard. Well, not a junkyard, a Thorlabs yard, and receiving, an assignment, build this apparatus. And the apparatus is kind of like an airplane, like in size and complexity. And so together with him, we've worked side by side for all these 6 years to get the experiment to work and to bring it to the level that it is now. And so I'm very grateful for having him there for all those years. And many of you are in the audience. I'm glad that I can see you once more. And of course, I want to especially thank the current members of the lab, Edwin, Chi, Megan, Simone, and Zhang, in whose eminently capable hands I'm very happy to be leading this. I like graphs. As a function of the year, this is the number of people in the lab, not counting Claudian, but counting me. And so as you can see, we've had 4.42 average lab members with a standard deviation of 1.7. So it's been a really wonderful group of people. I think we've had something like 25, 26 lab members, and they've all been really great. So next I want to thank, also, those posts and mirror mounts are not cheap. So, then I want to thank my thesis committee, especially Vladan, for his endless optimism and his willingness to discuss the physics underlying the thing we're trying to do, up to the point that it is necessary to discuss and to figure out, and they kind of push me along to see that I'm wrong without just telling me that I'm wrong. I think that's a very admirable skill, and I'm very grateful for it. I'm also very grateful that he gave me the opportunity to work on this project, which, I mean, it's exactly what I want. So, thank you. Then I want to thank the entire voltage group outside of our lab, especially Christy, Dorian, and Alexei, who were kind of a couple of years above me and really, helped me out and basically taught me a lot of the lab skills that I have, and were always there to encourage me and to give me advice, even when I was young and inept. Then CUA friends, especially Jesse, who might be for many philosophical discussions of great entertainment and destroying grinders late in the evening in the machine shop. And then I want to thank my MIT physics friends who came in with me back in 2011, and we had many great times together, went all sorts of places, hung out, drank beer, talked about physics, talked about non-physics. It was great. There's MIT staff that's really wonderful people, and I benefited from many of them. I especially want to thank Kurt, Mark, and Bill. So Kurt taught me everything I know about fabrication, which was critical to our project in a certain stage. Mark is our favorite Egyptian machine shop manager. He taught me everything I know about machining. And Bill is the house mechanic of the RLE, and he basically built our lab, except for all the optics and lasers and stuff. But like the infrastructure was thanks to him. Next, I want to thank my friends from Sydney Pacific, as you can see, and really could not fit more people. So Sydney Pacific, for those of you who don't know, is a graduate's residence at the intersection of Sydney and Pacific Street. And it's a really strong community, and it's full of really caring, wonderful people. And I've really been lucky to make friends with so many of you. And, it gave me there's a saying that friends are family you choose. And I think this is a very good example of that. In addition to my duties as a PhD student, I also did some extracurricular things, many of them at Sydney Pacific, which you guys know, but I also helped organize a very large event, which happens on campus, the MIT Career Fair last year. It was a lot of fun, and I think it really helped reinforce this belief, which is no longer a belief, this knowledge, that there is an attitude of perseverance in the face of challenges and the ability to come together with a group of people to make something happen, even if it seems practically impossible to do so. So next, I've also really enjoyed working with my colleagues in the Graduate Student Council and trying to advocate for small but long-term changes that make MIT a better place for all of us. Finally, the most important people in my life, my family. So my parents, Lena and Elena. My dad is here, happily recording. My brother Mark, his wife Anna, and his daughter Eva, as well as my lovely fiance. And with that, thank you very much.
Well, I may have proven Boris wrong a few times without telling him directly, but he's one of the students where I can truly say that I've learned more from him than he has from me. It has been a wonderful time, and I will really miss you as an intellectual sparring partner in quickly finding the flaws and new ideas behind these things. So the format is we will take questions from the audience, and then after that the committee will ask some more questions of Boris. For now.
This isn't really a question, but maybe it is. 50 years ago, when I was building the hydrogen maser at Harvard, in the maser laboratory, we had a cuckoo clock on the And the purpose for that was that the maser was very precise, but the Kugel clock was very reliable. And would you like to comment on the
Yeah, so
practical aspects?
of course. So you kind of saw this in the diagram I showed of the accuracy versus precision of different clocks. Basically, for a lot of these clocks, what limits them is eventually the grad students get tired, the lasers fall out of clock, and so if you look at the really state-of-the-art, lattice clocks, they're averaging, after which they get tired of comparing, is 1 day. 1 day is how long grad student can go without doing the home. So in that regard, the optical clocks are definitely not at the level of reliability of your Kugel clock. But the microwave clocks that we have now are extremely reliable. Right? They work for years at a time with no breakage. National labs have arrays of them. You can just buy them commercially. And for GPS satellites, they launch them on rockets to space, and they work there for years at a time. Although I know that for GPS satellites, I think they have 4 clocks on each one, and there's a few satellites that are down to their last clock, and they were launched 20, 25 years ago, so that kind of gives you an idea.
So do you see a future for that?
I mean,
for optical clock?
As the older generation in the room can attest, before we had nice diode lasers, we had horrible dye lasers, and you have to hit those with a hammer to get them to work, and now you don't have to hit them with a hammer. So maybe in another 10 or 20 years, there will be lasers that you can just turn on, and they always work and lock them reliably. And in that case, I think it will be just as reliable as the Kugel clock.
Yeah. So you're optimistic that these will?
Oh yeah, for sure.
Very good.
Beginning of your talk, you mentioned optical lattice clocks. You put all these atoms into the Land-Vicky regime where there's no Doppler shift, stuff like this. What else? So most of your experimental work has been on the squeezing aspect, I guess. What else do you have to put into the system to kind of get the whole clock to work?
Okay, so basically, if all you want to do is build a clock, then you really need to do basically only a few things. So you need to make a bunch of cold atoms. You need to have an optical lattice, which is just a laser with the right wavelength. And you have to have the clock laser. You have to align the clock laser to the lattice laser. And in that case, you can essentially do the Ramsey processing. You also need a way to measure the final state. But because the clock state is so long-lived, you can just do fluorescence in the ground state. So that's it. So building a clock, the real technical challenge of building a good clock is twofold. One, building a really good clock laser, and two, having a way to characterize and suppress the systematic shifts that your clock, that the atoms undergo when they're in the line.
Maybe a follow-up question. I think I maybe even know the answer, but with an optical lattice, unity field lattice, there's no, there's certainly a number limitation between how many atoms you have within the active area.
Right.
Is that a problem or not really at all?
It's definitely a problem. So in the strontium lattice clocks, they see effects of atom-atom interactions.
Yeah.
So these are ultra-cold fermions, so the S-wave collision is 0.
Yeah.
But they have P-wave collisions even when they're really cold. And so, for example, in the strontium clocks, when they overfill the lattice, so if you increase the density by a factor of 10, you get clock shifts that are on the order of tens of hertz, which again is tiny, but not as
Maybe I'll ask a question, if I may. To bring up the overview slide.
Which one?
From the review paper,
Ah,
all
yes.
the squeezing things.
Yes, just one second.
So you showed the point that you have measured so far.
The other one. Okay. Where's this one? I turn it off. There we go.
So care to make a prediction for Edwin, G, the Yang friends, where they should be linear?
I mean, I think that with the right measurement-based squeezing scheme, we can definitely go at least to 10, even where we are now, maybe like 15 with a few thousand atoms. With the unitary-based squeezing, I mean, I honestly think that with maybe about 1,000 atoms and the right kind of probing scheme, we should be able to get to near the Heisenberg. So like 20 or 25. like off the charts here.
I put this graph into my NSF proposal and I wanted to see if you agree with me. So pop quiz. Catching arrows. So I think we're on the same page. I think it's an enormously promising proposal, but it's very difficult to explain. Other? If not, then let's thank Boris again. Ask you to wait outside.
Somebody